Today I will be talking about videostorm, a video analytics system that could scale to process thousands of live video streams in large clusters. This work is done with my collaborators from Microsoft. Video cameras are pervasive. Major cities all over the world, like New York City and London, have millions of cameras deployed. IoT devices with cameras are installed in buildings for business intelligence, and those installed on streets are used for crime prevention and traffic control. In fact, we are working with the city of Belleville, among others, for traffic planning and safety using their traffic cameras. The key to achieving the potential of these cameras is effectively analyzing live video streams. Many types of video queries are developed for this purpose, such as counting cars for smart traffic light control, toll collection by reading car license plates, tracking child abductors in Amber Alerts, recognizing faces when people are around your doors, and so on. A video query can typically be represented as a pipeline of transforms. As an example, here is a query pipeline for car counting. At the beginning, a video stream is decoded to individual frames by a decoder. This component might also decide to lower down the frame rate or resolution based on your resource limit. Then the frames go through a background subtraction module, which maintains a background mask based on steady video content. You can also do the same thing with a DN object detector. By subtracting the background, the tracker module could identify the foreground moving objects and count them. The purpose of using a tracker is to make sure that cars in continuous frames are not double counted. However, running vision algorithms can be very expensive in their resource usage. For example, the best car tracker from the VOT Challenge 2015 could only process 1 frame per second on an 8-core machine. Some of the most accurate deep neural networks for object recognition require 30 G-flops to process a single frame. Because of the high processing costs and high data rates of video streams, resource management is crucial. When running a lot of video queries in large clusters, it's important for us to think about how to reduce the processing costs of individual frames and how to manage resources across multiple frames. However, a key property here is that vision algorithms, by their very nature, are approximate. Because of factors like camera angles and video content, even the best license plate reader cannot possibly read all license plates when they are dark and far, and even the best face recognition algorithm cannot possibly detect all the faces in a crowd of people. So vision algorithms typically contain various parameters, and we call them knobs. Examples of knobs are video frame rate and resolution, and some internal algorithmic parameters, such as the size of sliding window for searching object in object detector and the distance mapping metric for object trackers. We call a combination of these knob values the configuration of a video query. Changing the configuration parameters or tuning these knobs will have impact on both resource usage and quality. For the license plate reader, if we sample the frames to get 3 frames per second and run it at 720p resolution, it could identify and read license plates in high quality with 93% accuracy. However, this also requires much more computation resource. On the flip side, if we sample the frames to process only 1 frame per second, run it at 480p resolution, and then with this configuration, the quality of reading license plate is much lower, it's 57%, and sometimes it could also miss some cars. The resource usage is also lowered down to only 0.09. All these knobs have different impact on both resource usage and quality. So in this case, if we fix all other parameters and only tune the frame rate knob, here we can see how the resource usage and quality changes. The x-axis shows the frame rate varies from 3 to 14 frames per second. The blue line shows the quality changes from 0.3 to 1, and the orange line shows the CPU usage changes from 0.05 to 0.4. When tuning all these knobs to different values, here's how the quality changes in blue and how the CPU usage changes in orange. Some of these knobs are discrete, some of them are continuous. In fact, when tuning all these knobs together, it's not rare to see that the resource and quality could change orders of magnitude. For example, here we explore all the different combinations of the 3 knobs in the license plate reader query. The graph has a resource demand on the x-axis in log scale, and the result quality is on the y-axis. If you examine the 2 points in red here, oftentimes there are choices that give us only a small reduction in resource quality and help us save a lot of computation resource. And based on these results, we know that it's hard to infer the quality and resource usage without actually running these video queries. Please note that this is very different from approximate SQL queries, where you can directly predict the quality and computation time based on the sampling rate. In fact, there is no known analytical model to infer these numbers for video queries. While many queries require producing results in real time, some queries can tolerate a lag, which is a time difference between the arrival and processing of a frame. In fact, video analytics queries have a wide variety of different quality and lag requirements. For example, license plate readers at toll routes typically require high quality results but can tolerate a lag of even hours because the billing must be accurate but can also be delayed. A query counting cars to control traffic lights can work with moderate quality and get approximate car counts, but it will need the result in very low lag. However, the same license plate readers, when used for Amber Alerts, require high quality with almost no lag. So to summarize, there are 2 metrics we care about for video queries, the quality and lag. However, we cannot directly control them. What we can directly control are the configurations and resource allocation for each queries. For example, the configuration determines the quality, and the resource allocation could help us catch up with the lags. Our goal here is to configure a set of parameters exposed by vision algorithms and enforce the resource allocation on these video queries. By doing that, we want to maximize the quality and minimize the lag across a lot of vision queries within the resource capacity of the cluster. There are also several challenges, as we mentioned before. Vision algorithms expose multidimensional knobs, thus a huge configuration space, and there's no known analytical model, so it's hard to directly predict the resource usage and quality impact for different configurations. Also, compared to traditional data analytics queries, video queries has a wide variety of different quality and lag goals. When scheduling queries on a shared cluster, it's challenging to jointly optimize for quality and lag at the same time. In the next few slides, I will show you how our system, videostorm, deals with these challenges and achieves our goal. To give you an overview of how videostorm works, here is a high-level workflow. When users submit a query to the system, it first goes through a profiler to generate a resource quality profile for the query. The user also provides a utility function. Together with the query profile, it then goes to the global manager, which schedules the queries to run many worker nodes. The scheduler will periodically reschedule the queries, including changing their configurations and reallocating resources among these queries. So just an overview, and I will explain this much further in a moment. The query profile builds a model that measures the quality and resource impact of different configurations and also reduces the configuration space significantly. So that will solve our first challenge. And the online scheduler will jointly optimize quality and lag among multiple queries based on users' need. So this will solve our second challenge. We can divide this workflow into 2 parts, the offline profiling and online scheduling. And let's look at the offline profiling first. So a query profile is defined as a mapping from the configuration to resource demand and resource quality. The profile is computed either against a labeled dataset or with the result of a golden configuration, which means that if you run the video at its original 1080p resolution and 30 frames per second, this is known to be very expensive, but it will give you the highest possible quality. The profiler estimates the query profile by greedy exploration of the configuration space. Here we use the x-axis to show the resource demand, which is the number of CPU cores in log scale, and y-axis to show the aggregated result quality. For each configuration, we run the query on the dataset, calculate the average resource usage and the average quality relative to the ground truth. And each blue point here is a result of one certain configuration on the entire license plate dataset. We can see that towards the left, the configurations are more efficient in their resource usage, and towards the top, the configurations give you more accurate result. Specifically, let's look at the orange cross here on the plot. This configuration is not optimal because it can be further improved in both resource efficiency and quality. And in fact, the red cross here is a strictly better configuration in both resource efficiency and quality, which makes the orange configuration not useful in practice. We call the red configuration Pareto optimal because we cannot further find configurations that can increase resource efficiency and quality without hurting the other. The dashed line here shows the Pareto boundary of all such configurations for the license plate query. We extract the configurations on the Pareto boundary and use it as the resource quality profile for this query. This reduces the number of configurations that need to be considered by an online scheduler from thousands to only a few. This effectively solved our first challenge by measuring the resource and quality impact of different configurations and then providing only a few configurations for best resource quality trade-offs. So after offline profiling phase, we get a resource quality profile. And then let's look at the online scheduling part. To deal with various requirements of quality and lag of video queries, we use the utility function to encode the goals and sensitivities of quality and lag. We let users to set the minimum required quality and their maximum tolerable lag. Utility function is a weighted combination of achieved quality and lag. It rewards additional quality above the minimum quality goal, and it also penalizes the additional lag that is longer than the maximum tolerable lag. In this online phase, we schedule for two natural goals: maximize the minimum maximize the minimum utility, or maximize the total utility. The former achieves better maximum fairness, which is probably what you want if you run videostorm in a private cluster. The latter achieves better overall performance, which is good for running videostorm in public clusters where the revenue is directly associated with the user's utility. Based on the stats information collected from the workers, the global scheduler will periodically reconfigure and reschedule the queries running in the cluster. During a resource shortage, the resource allocated to a query might be less than its demand. And in this case, videostorm scheduler will allow frames to be accumulated in front of a query and then later on catch up when the resource is sufficient. With this utility function and the performance-based scheduling, we solve the second challenge by jointly optimize quality and lag among multiple queries based on users' need. To give you an intuition of how this works, assume that there are two queries, a blue one and an orange one. The query can tolerate a lag of up to 8 seconds. When running on a constant video stream given 1, 2, 3 CPU cores to the blue query, it produces a result with 0.6, 0.7, and 0.8 quality. With 1, 2, 3 CPU cores allocated to the orange query, its quality varies much more. It produces 0.1, 0.3, and 0.9 quality. We name the configurations as configuration 1, 2, 3 for these two queries. We launched the two queries on a 4-core machine, and at time 10, the number of available cores is reduced to 2. This could happen when videostorm is co-located with some other kind of workload or some high-priority queries come in. And after another 12 seconds, the available resource is back to 4 cores. If we use an existing cluster scheduler, such as Yarn and Missiles, they focus on resource fairness. So what this scheduler will do is to evenly split the resources to these two queries and then pick the best configuration without incurring any lag. The graphs here all have time on the x-axis. The first graph shows how the resource is divided between the blue and the orange queries over time. The middle graph shows how the quality and lag changes for the blue query, and the bottom graph shows how the quality and lag of the orange query changes over time. We can see that at the beginning, each query has 2 cores. Choosing the second configuration for each query, the the quality of the blue and the orange queries will be 0.7 and 0.3 respectively. Then during the resource shortage, their configurations are lowered to C1, and they will get quality of 0.6 and 0.1. After another 12 seconds, the cores are back, so their configurations will be back to the second and get quality of 0.7 and 0.3. However, based on the property of these two queries, we can see that the additional core could be shifted from the blue query to the orange query, and this will only lower down the quality of the blue query by 0.1, but boost the quality of the orange query up to 0.9. So what a quality-aware scheduler will do is to only allocate one core to the blue query and all the other cores to the orange query. As a result, the quality of the blue query stays at 0.6, and the quality of the orange query started at 0.9 with configuration 3. When the allocated resource is down to 1 unit at time 10, the scheduler chooses not to change the configuration of the orange query, and the quality keeps unchanged at 0.9. Because at this time, the demand of the orange query is 3 cores, but only allocated with 1 core, so the lag will gradually grow up to 8 seconds, as shown by the green line at the bottom graph. At time 22, the resource is back to normal, so the scheduler will choose a lower configuration C2 to allow the query to catch up with the video. We see a temporary drop on quality, then it's back to normal 0.9 and quality and 0 lag. Comparing the two schedulers, the fair scheduler achieves a total quality of 1 in normal case, but the performance-based scheduler will achieve a quality of 1.5, which is 50% higher. Here I will also briefly mention some additional features of videostorm. We see that Profiler could help us improve the efficiency of scheduling. However, using an incorrect profile could negatively impact the scheduling. This could be because of machine processing power, video content, and so on. videostorm scheduler is robust in handling these errors with an online resource adaptation logic. So this will make the videostorm scheduler performs nearly the same as the correct profiles in practice. videostorm also provides a smart placement and migration strategy and also a hierarchical scheduling structure to improve efficiency and scalability of the system. And we recommend you to read our paper for details. We evaluate our system on 1 scheduler node and 100 worker nodes running on Microsoft Azure Cloud. 4 types of queries are used: license plate reader, car counter, DNN object classifier, and car tracker. The workload is a video dataset we collected from the cities we partnered with for 2 months in 2015. We streamed the recorded video at their original frame rates and resolution to mimic the live video streams. We started with running 300 queries on 100 worker nodes. The 300 queries are from the 4 types of queries that I just mentioned. 40% of them has a stringent lag goal of 20 seconds, and 60% of them can tolerate 300-second lag. The 3 types of queries, the 3 queries here have the 3 graphs here have time on the x-axis. The top graph has a share of cluster CPU by the 3 types of queries on the y-axis. The middle graph has a quality, and bottom graph has a lag on the y-axis. At the beginning, there are only group 1 and 2 queries, and they will share the CPU resources, running at a high quality and incur no lag. At time 50, we add additional 200 license plate reader queries into the system to run for 150 seconds. This is to mimic an Amber Alert. All these 200 queries are lag sensitive and require high quality. As a result, what a videostorm scheduler will do is to allocate dominant amount of resources to this type of queries. From the middle graph, you can also see that the scheduler lowers down the quality of the queries that have lower quality goals, and also delays the queries that have higher lag goals as much as possible. At time 200, the bursty queries are gone, and the scheduler will allocate the resources to let the queries to catch up with their videos. We see that the system's workload highly depends on how long we run these bursty queries. And compared to the results of a fair scheduler with different bursty durations, a videostorm could achieve up to 80% improvement in quality and 7 times better lag. Since videostorm needs to reschedule and reconfigure frequently in reaction to all dynamic changes in video queries, we want to measure whether the scheduler is efficient enough to make scheduling decisions in short time. Here we see the numbers of queries on the x-axis and the scheduling time in seconds on the y-axis. Lines with different colors are different sizes of clusters that we tested our system on. Even with thousands of queries, videostorm can make rescheduling decisions in just a few seconds. And combined with the low latency action, we believe videostorm is sufficiently scalable and agile. Finally, we will show a key feature of videostorm. It's robust to query processing errors. As mentioned before, using incorrect profiles can negatively impact the scheduling performance. And as an example, here we pick a query and run 3 copies of it. They have exactly the same demand, and only with 1/3 of the total resource allocated to each query could they meet their quality and lag goal. But in this case, we purposely changed the resource demand of one of the queries to be twice as much as the true value, and another query to be only half of the true value, without telling the scheduler the actual true values. And in this graph, the x-axis shows the time, and the y-axis shows how the resource allocated to these 3 queries change over time. We can see that without adaptation to errors, the query with half resource demand in purple line gets much lower resource than what it should have. videostorm adaptively keeps track of a missed estimation factor, which is a multiplicative error between the predicted resource and the actual resource usage. With this adaptation logic, we can see that our resource allocation converges to the right allocation soon after we start running these 3 queries. This is because if you look at the graph on the right, the missed estimation factor quickly converges to 2 for the halved query and 0.5 for the double query. With this mechanism, videostorm could perform nearly the same with erroneous profiles. To conclude, videostorm is a vision analytics system that could scale to process thousands of videos in large clusters. It has an offline profiler that efficiently estimates the resource quality profile, and it has an online scheduler that could jointly optimize for quality and lag. videostorm is currently being deployed and running in Belleville City, and soon will be deployed in many other cities. So thanks for listening, and I'm happy to take any questions.
Hi, I'm Wonsu from NetApp. So the part that you talked about scheduling, it reminds me of sort of real-time scheduling theories. So is this the hard real-time system or the soft real system? What I mean is, can you always guarantee that you'll finish the work that actually when you promised to do?
Okay, so the question is whether this is a deadline-based, whether the deadline is strict or not. So in this case, we don't set strict deadlines. So what we do is to let the user to set their maximum tolerable lag. And this is something that that the scheduler might violate, but it will receive a penalty if it exceeds the maximum tolerable lag. Yeah.
So it's basically soft real-time.
Soft, yeah.
Thank you.
Mm-hmm. Hi, I'm Yiming from Tsinghua University. And I have a question about the utility function.
Right.
So for users without expert experience, the thresholds can be hard to set. So is there any solution or just heuristic method to set it?
Good question. So the question is whether the various parameters in the utility function will be easy to set for users that are not experts. So the actual utility function, which you can find in the paper, will have 4 parameters that you need to set. So what we find will be useful in practice is to discretize these goals and sensitivities. For example, we only allow users to choose from a predefined set of lag, for example, 1 second, 10 second, 100 second, and we let them to choose their minimum quality also in this fashion. So this is very similar to what the cluster providers will let you do. For example, Microsoft Azure or Amazon EC2 will not allow you to like set arbitrary combination to spin up the VM, right? So there are only fixed options, and we find that work pretty well in practice.
But discretized value can may not support all the situation. So
right, exactly. So so in this case, we only want the users to give high-level goals and sensitivities to the system, and the users can always tune these parameters and change them later online, actually.
Okay, thank you.
Hi, I'm John Emmons from Stanford. So my question is about the profiler. It seems like it generates a configuration for a particular video. Have you considered sharing configurations across videos, or at least using it to bootstrap configuration so that you don't need to fully explore the space for each new video?
Good question. So the question is like whether we can generalize the profiles that are done on one video to many cameras. So this is the general answer is that it depends on the video content, and because the query is specifically profiled and tested on one specific camera, and the actual resource usage quality will also depend on the video content. For example, like even if a street is always very busy, you cannot use a profile on this camera and directly apply it on another camera, which is probably in some small community that have very small number of cars. So in this case, we will we will generate the profile separately for different cameras. But in some cases, if you find the situations that are similar, you can also directly adapt that profile. Yeah.
Thank you very much.
Okay, let's thank the speaker again.